Hi, my name is Denali Pinto. For this problem, I will be covering learning outcomes 1A, 1B, 1C, and 3. The goal of this problem is to calculate the total heat transfer rate as well as the temperature on the inside of the airplane window by using resistance networks. Here, the thermal conductivity of acrylic and the thermal conductivity of air at the desired temperatures were looked up, and the thickness of the windows were looked up as well. Steady state was assumed, as well as constant K and H and one-dimensional heat transfer. The outside convective resistance and radiation resistances were drawn in parallel, with the rest in series. This resistance network diagram shown here shows learning objective 3. Summing these resistances applies learning objectives 1A, 1B, and 1C for conductive, convective, and radiation heat transfer mechanisms. To find the heat transfer coefficient for radiation, the emissivity and the Stephen-Boltzmann constant were used. The overall heat transfer rate was determined to be 13.6 watts, as the inside and outside temperatures are given. Then, using the convective heat transfer mechanism again, the inside window temperature was determined to be 4.95 degrees Celsius. The sources for the various properties are listed below here. This problem will cover learning outcomes 2A, 2B, 4A, 4B, 4C, and 5A. For the first part of problem 2, you are asked to find the steady state 1D heat conduction equation and use it to find the temperature at the bottom of the lasagna. You are given the thickness of the lasagna, the thermal conductivity of the lasagna, which is that of beef since it is a beef lasagna, and the heat flux in the oven, as well as the temperature of the lasagna and the oven. Assuming 1D steady state, constant K and H, no radiation, and no heat generation, you use an energy balance in Cartesian coordinates, which covers learning outcome 5A. Then you find the energy balance and simplify with those assumptions, deriving the differential equation in which is learning outcome 2A. Integrate this twice and apply your two boundary conditions, and you find your temperature at the bottom of the lasagna. Solving this shows learning outcome 2B. For part B, you are given the convective heat transfer coefficient and the time that you leave the lasagna in the oven, as well as the density and specific heat of the lasagna. You can assume the temperature of the lasagna is constant throughout, meaning you use lumped analysis. You also assume steady state, no heat generation, and constant K and H. And using the corrected length, you can calculate the temperature of the lasagna after 30 minutes. This demonstrates learning outcome 4A. For part C, you realize that your lumped analysis wasn't acceptable after taking a bite of the lasagna and finding it cold. So you use multidimensional analysis. You still assume steady state, no heat generation, and constant K and H, and use the 1D analysis equations for your three-dimensional analysis. The Biot number for the height of the lasagna is 1, which is greater than 0.1, demonstrating why lumped analysis wasn't appropriate. You use table 4a to find lambda 1 and a1 and repeat this process for the width and length of the lasagna. You calculate theta for the z direction, y direction, and x directions separately, which each show learning outcome 4b. And then you multiply them together for three-dimensional analysis, which is learning outcome 4c. And here the references are shown.